Okay, I guess we'll go ahead and get started for class today. It's Tuesday, March 23rd. This is Civil Engineering 481, Transportation Engineering, and today we're going to be talking a little bit more about Chapter 6, and we are going to talk about multi-lane highway segments as opposed to freeway segments, which is what we talked about last Thursday. And we'll do a little bit about two-lane highways as well, not too much, just a little bit. There's a section in your textbook on two-lane highways, but we're going to spend just a very short amount of time on that particular topic. So before I get started, I have to note, I think one of the last things I said on Thursday was good luck to the Aztecs, and it didn't help, obviously. Didn't help at all. The Aztecs played their worst game in 2 years last Friday night. And it happened to be on national TV in the first round of the tournament. So I was very disappointed by that, but that's just the way it goes sometimes, especially with San Diego sports. We always seem to have a difficult time. So anyway, hopefully I just read the story this morning that our coach is going to stay. There was some talk that he might go back to his alma mater, but he's staying, so that's good news. We'll continue to have a good team. Hopefully next year we'll come back even stronger. At least I hope so. Anyway, yeah, it was a sad game. That was one of the comments. Okay, so I just had to acknowledge that. A couple of other things before we get started here. There are two things that just posted in Canvas. Number one is the homework assignment for Chapter 6, which is not due until April 1st. And as a matter of fact, I might even adjust that to April 2nd, because next week there is a rest and recovery day, which is March 30th. A week from today, next Tuesday, we don't have class. So just so that you note that in your schedule. And then the day after is Cesar Chavez Day, which is also a day with no classes. So there's a couple of days off next week. And I think I will adjust the homework to be due by Friday, April 2nd, because they're suggesting that there's no assignments due on either side of the rest and recovery days. And I guess Cesar Chavez Day is kind of considered, because it's paired with a rest and recovery day, it's kind of like 2 days off. So instead of having it due the very first day after that, we'll make it on Friday, the 2nd. I'll adjust that in Canvas. So I will do that. But the other thing I've done that I've added to Canvas that just posted at 4 o'clock as well is the next group assignment. If you looked at your syllabus, our next group assignment is on Thursday of this week, on the 25th, just a couple of days away. And I posted what I did there is I picked out a couple of problems that are in your book for Chapter 6. And I'm asking that you do these 2 problems as a group, just like the first group assignment where we had, there was 4 homework problems that I asked you guys to do as a group. This time it's just 2 problems. And each of the problems that I picked, problem 14 and 614 and 620, have 2 parts. And I think they're good problems because they basically ask you to assess the level of service for and problem 614 is a freeway problem and problem 620 is a multi-lane highway problem. And the problem asks you to assess the level of service before and after an adjacent development is built, which is pretty, fairly real world. That's what traffic, a lot of times traffic studies are done and traffic analysis is done to support the approval of development projects, whether they be commercial or residential or whatever. Oh, hold on a second. Somebody says they don't see them. I'll take care of that right now. I know what I did. Yeah. Oh, no, wait. These are assignments. They should be posted in assignments. Let me see. Oh, no, I didn't publish them. Okay, there we go. That's the problem. I set them to be posted at 4 o'clock, but I didn't publish them. They're now good. Thanks for letting me know that. They are now up on Canvas in the assignments section, the homework for chapter 6 and the second group assignment. Thanks. Okay, got it. Anyway, so these two problems, I'm asking you to complete them by 4 o'clock on Friday, in other words, by the end of the week. And as last time, you can use the class time on Thursday if you want. And this time what I'm going to do is I'm just going to establish 10 breakout rooms. If your groups decide you want to use the breakout room that I set up, you can use it. Last time, I think there was one group that used a breakout room during the time, but you don't have to. You can get together however you want to as a group, whatever works for all of you. But on Thursday at this class time at 4 o'clock, I'll have a breakout room available for you. And just, if you're group number 4, use breakout room 4. I'll have 10 of them set up. They don't all have to be used, but that's one way you could do it. I think as a group, you could get these two problems done in an hour. They're not super complicated, but I think they're good problems to be familiar with how level of service works before and after putting in a development adjacent to either a freeway or a highway segment. So you can see I wrote what you need to do for the assignment into Canvas there. And so it's just a matter of getting your group together and submitting one solution set for the two problems, by Friday, so very similar to the other group assignment we did a few weeks back. Should be pretty straightforward. You can decide how you want to split up the work amongst your group. One thought might be that each of the two problems kind of splits into two pieces, right? There's calculations you have to do before the development's in and calculations you have to do after the development's in. So it might be a way to at least split the two problems into 4, and you can have, but it's all up to you as your groups as to how you do it. Bottom line is you just post the solutions for the two problems by Friday at 4, and then I'll grade them just like I did the previous time. And then the homework assignment, which is 4 problems from chapter 6, those aren't due until a week from Thursday, or excuse me, a week from Friday. I'm going to adjust that, April 2nd, so that you have plenty of time to work on those problems. And if you look ahead to our schedule that's in your syllabus, today we've got, we're going to finish up the multi-lane highways for chapter 6. Thursday, I'm going to allocate that for the group assignment. If you want to use that time on Thursday, you can. You don't have to, but you have to have the problems in for your group by the end of Friday this week. Then next Tuesday is a rest and recovery day. And then next Thursday will be a regular class where we will review chapters 5 and 6 ahead of the second midterm, which is the following Tuesday, April 6th. All of that's on your syllabus schedule. So that just kind of lines things out for the next couple of weeks. Our next midterm, which will be on chapters 5 and 6, will be 2 weeks. That's 2 weeks from today, right? Yeah, 2 weeks from today, April 6th. Okay, so any questions about what's upcoming and the group assignment, the homework assignment, the schedule? Once we get past the midterm for chapters 5 and 6, we're kind of in the stretch run of the semester. We have 2 more chapters to go: intersection analysis and traffic forecasting. You'll have your group papers due at the end of April, and I've allocated 2 class periods for presenting those papers. Yeah, before you know it, we're going to be heading towards the end of the semester. This stuff goes fast. So, any questions before I get started on today's material? Okay, I don't see anything in Zoom, so I think I'm going to go ahead and get started. I'm going to share my whole screen, and I think you'll see why in a second. Okay, and let's see here. All right. Keep that right there. Okay, what I have here are the slides on the left-hand side of the screen, and then I've also got the key equations over here on the right, and I'm going to move up the equations to the multi-lane highway segment here. Let me just adjust my screen so I can see it better. There we go. And so we've got pretty much a handful of equations in the multi-lane highway section of chapter 6, but we will refer back to a few other equations up in the freeway portion because there are some factors that are the same for both types of analysis, and you'll see as we go through it. So anyway, last Thursday we talked about freeways. Now we're going to talk about multi-lane highways. So what are we talking about when we talk about multi-lane highways? Generally, we're talking about larger highways. You know, a good example of a multi-lane highway that's not a state highway, as a matter of fact, would be like Friars Road. You know, Friars Road, you know, is a pretty major road, the one that goes by the completely flattened stadium. I'm sure all of you have seen that. It was in the front cover of the paper that the stadium has been pretty much completely torn down now to make room for San Diego State, which is great, but it's kind of sad. I sent a picture to my boys about, you know, I've been to that stadium, I don't know, probably a couple of hundred times over the years for different sporting events. So anyway, but Friars Road would be a good example of a multi-lane highway. A state highway that's more like, that operates a little bit more like a multi-lane highway would be if you go up into the North County from Oceanside, not 78. 78's a freeway from 5 to say 15, but 76 up in Oceanside, if you go up a little bit further north, it's technically an expressway, but its characteristics are like a multi-lane highway because it has signalized intersections and so forth. So anyway, so what are some of the characteristics as listed here? Their speed limits are generally between 40 and 60 miles an hour. Excuse me. You can sometimes have some multi-lane highways that are higher speeds that are in essence the same speed as freeways, but most of the time the speed limits are between 40 and 60. They have 4 or 6 lanes. I think Friars Road might have 8 lane sections in it too, which is unusual for a multi-lane highway to have 8 lanes is pretty rare, but it does happen. And then they often have, as it says here, physical medians with two-way left turn lanes, TWLTL. I don't know why they have to put it that way, but anyway, two-way left turn lane in the medians. And in some cases, and this is important, that's why I have it highlighted, some cases multi-lane highways are undivided. And you'll see when we start getting into the calculations whether a multi-lane highway is divided or undivided makes a difference in how you evaluate it. They're often located in suburban communities. And they can be, you can find multi-lane highways in high volume rural corridors. Like, you know, those are usually corridors that connect maybe 2 cities. So the 2 cities are very urbanized, but the connecting highway between them isn't. It may run through a rural corridor to connect the 2 cities, for example. Traffic signals oftentimes are found on multi-lane highways. It says, although traffic signals spaced at 2 miles or less typically create urban arterial conditions, which urban arterials are a little different. They're less, those roads are at lesser design standards than the multi-lane highways that are between 40 and 60 miles per hour. But generally there can be signals on multi-lane highways, but they tend to be spaced apart. They tend to have longer spacing than in like highly urbanized areas where you see, you might have 4 traffic signals in a 1 mile segment or something like that. Okay, what things that make multi-lane highways different from freeways. So first and foremost, vehicles enter and leave at intersections and driveways, and they can go through the median. You can't do any of that on a freeway. There's no intersections, there's no driveways. I mentioned that last week, that maybe the only kind of driveway you would have is to some sort of maintenance station or something. But multi-lane highways, definitely you can enter them from intersections and driveways, and you can go through the median at various points. Traffic signals can be on the facility. Remember, on freeways, the signals are only at the ramps, where the ramps tie into the local road, but they're not out on the freeway itself. And the design standards of multi-lane highways, as it says here, tends to be lower than what you find on freeways. But as it says, the ideal multi-lane highway approaches freeway conditions as you have fewer access points and less turning and less friction, let's say, to the traffic flow. And the visual, as it says here, the visual setting and developed frontage along multi-lane highways have more impacts on drivers. That's because, think about Friars Road. There's shopping centers right up against the road, as you're going in and out. So there's a lot of what I call friction in the traffic. You've got to be very aware as a driver of all of the interactions, vehicles coming and going, making turns, coming in and out of driveways, that sort of thing. You don't have any of that on freeways. Basically, freeways, the only places where you have that kind of friction is in those weaving areas we talked about last week. So here's a few equations, and when you look at these equations, they'll remind you a little bit of the equations that we worked on for the freeways. But the break point, that there is the one thing that we had in the freeway equations, there was the BP, or the break point, and there was an equation for the break point. But when it comes to multi-lane highways, the break point is singular. It's 1,400 passenger cars per hour per lane. So the break point is the same for all speeds on a multi-lane highway. For freeways, the break point was different for different speeds. And if you look closely at the figures, you'll see the difference. And so therefore, there's still a capacity calculation, a C calculation that is that here, equation 613 for multi-lane highways, but there's no break point equation for multi-lane highways, because the break point is 1,400 in all cases, okay? But you can see this equation here is a little, looks similar to equation 6.2 for the freeways. As a matter of fact, I got 6.2 listed up here, I think. Yeah, see, you can see the freeway equation. It's similar, but it's like, it's got break point, BP, in the equation, rather than, and here it's 1,400. And the power that it's raised to, that the equation is raised to, is different than the power that it's raised to here. So again, empirical equations that are created through the highway capacity manual. But one thing I will just tell you right now, I've done, this is my 3rd semester teaching this class, so I've done it 2 semesters. And in the previous 2 semesters, it happens, homework and even on the exams, I think. Remember what you're working on, whether it's a freeway or a multi-lane highway. I mean, nothing's here to fool you and make you think it's a freeway, but it's really multi-lane, or vice versa. The problems usually are very clear. You're on a multi-lane highway or you're on a freeway. So be sure to use the right equations. Both semesters I had students that used the freeway equations instead of the multi-lane, or vice versa. So just you know, it sounds pretty basic, but just make sure that it's very clear which facility you're working with and analyzing, and use the proper equations, because of course you won't get the right answer if you use multi-lane equations for freeway segments. Okay, so that's the first set of equation. And see this this speed flow rate diagram looks like the one we had for the freeways, which was figure 6.2, I believe, in your book. But the thing is here, the break point, if you look right here at 14, here's 1200, 1600, right in the middle, 1400, you can see that the lines, the break point is the same for all different speeds, from 70 miles per hour all the way down to 45. The break point is 1400. If you go back and you look at figure 6.2, I'm not going to pull that up right now, but if you do, you'll see that the break point varies. That's why there's an equation to calculate the break point. But anyway, again, same thing. Make sure you're using the right figure. If you're going to use the figure to help you remember, there's a lot of good data here. There's the free flow speed, there is the densities, and there is the flow rate down here, and then you've got the regions of level of service A, B, C, D, E, and F. But if you're going to use the figure, make sure that you're working on a multi-lane highway for figure 6.4, and use 6.2, figure 6.2 if you're working on a freeway, okay? And then table 610, for the freeway, it's table 6.2 and figure 6.2 are the same, one and the same. One's table form and one is in figure form. Here, it's because it's later in the chapter, it's the figure is 6.4 and the corresponding table is table 6.10, 6.10. So these two are virtually the same data. It's just in table form because you've got your level of services, you've got your free flow speeds for each one of these segments, you've got the maximum density and the maximum flow rates for all of these. Okay. So the procedure that you use for multi-lane highways is very similar to the procedure that we went over last week for freeways. You establish the base conditions and capacity, you estimate or measure free flow speed, but that the way you do these things is a little bit different, and that's why we're going to go through some examples so that you'll see what the differences are between this and the freeway analysis. So you estimate or measure the free flow speed, then you calculate your analysis flow rate, or your V, this value here, V sub P, and then you calculate the density and determine your level of service. Remember, on the freeway calculations, everything was aimed for making this density calculation here at the end. The flow rate divided by the speed equals your density, and remember, level of service is measured by the density of the traffic flow. So this is what for the freeway, in order to find your level of service, you're trying to get the density calculation here. It's the same thing for multi-lane highways. Okay. So let's start getting into it. What are the base conditions for multi-lane highways? We went over the base conditions for freeways. The base conditions for multi-lane highways, again, are similar. Lane widths are 12 feet. We talked about that before. 12 feet is what you find in most places. And if you're going to narrow the lanes, you are going to suffer the consequences of a lesser capacity, because people don't like to drive in narrow lanes. And you all are drivers, and maybe you've never really noticed whether driving in a narrow lane has an effect on you. It's probably even subconscious as a driver in many cases. You don't like, it's not like you're driving along and all of a sudden you're like, wow, this lane's really narrow, I'm going to slow down. It's not, you don't, it's just it's almost a subconscious reaction as a driver, that if you're in a narrow lane, you're gonna drive more cautiously. So anyway, the 12-foot lanes, then a minimum of 12 foot of total lateral clearance from roadside objects. right shoulder and median. This is a little different. This is a different measure than for the freeways. The freeway only mattered on the right, the right lateral clearance because because of the fact that freeways always were divided. But anyway, lateral clearance or shoulder median greater than 6 feet is considered in computations to be equal to 6 feet. So you'll see this when we go over this particular factor that you use in calculating the free flow speed. These are all things that can have an impact on your free flow speed. So the traffic stream consists of passenger cars only. That's the same base condition that we used for freeways. No direct access points along the roadway. And I just got through telling you that multi-lane highways can have access points along the roadway, but the base condition is to assume that there's none. The base condition is to assume that there is a divided highway. And as I mentioned, that you can have multi-lane highways that are undivided. And the issue is if there are access points, if the highway is undivided, these things are going to have an impact on the free flow speed. They're going to have an impact on the factors that reduce free flow speed, and you'll see how that works. Once again, level terrain with grades no greater than 2%. That was the same base condition for freeways. A driver population of mostly familiar with roadway users. We talked about that, similar for the freeway. And then a free flow speed of 60 miles per hour or more. That's a little bit different than the freeway, but a similar kind of condition. So anyway, those are the base conditions. And then if any of those conditions vary, it's going to have an impact on this equation down here, which is equation, hold on, I have to, equation 614, which is the free flow speed equation for multi-lane highways. So you can see you start with a base free flow speed, and then you have these factors for lane width, lateral clearance, medians, and access points. And so we're going to go through all of those right now so you can see how each of those can have an impact on the free flow speed. So here's the equation, 614. And the one thing that you can see that this equation looks a little bit like, what is it, equation, I can't quite read the number, 6.6 up here for freeways, but it's not exactly the same. There's a couple of factors, one factor, the lane width factor, that's identical, but then you see instead of 75.4, you use this BFF, and it's not, the BFF doesn't stand for best friends forever, I don't think. It's basic freeway, basic free flow speed, or free flow speed for base conditions. So you can see the equation's similar, but there's different factors that you have to take into account. So we'll talk a little bit about the free flow speed for base conditions to use in the calculation. Then the adjustment for the lane width comes from table 6.3, which is back in the freeway portion of your chapter, because it's exactly the same. There's no change there. It's the same table, 6.3. But the adjustment for total lateral clearance is from equation 615 and table 611. And so it's different. That's a different factor. So you'll see that as we go through the example. Then there's an adjustment for median type from table 612. And then there's an adjustment for access point frequency, which is table 613. So you can see the equation's a little similar to equation 6.6 for freeways, but different factors, and we'll go through how you apply them. So the lateral clearance for multi-lane highways is table 611. And you use this equation 615, which basically says the total lateral clearance is the lateral clearance on the right and the lateral clearance on the left, okay? And so the lateral clearance is the sum of the lateral clearances of the median if if the median is greater than 6 feet, you use 6 feet. And the shoulder, if it's greater than 6 feet, you use 6 feet. Therefore, for the purposes of analysis, total lateral clearance cannot exceed 12 feet. And the issue is, if you have more than 6 feet if you have more than a total of 12 feet of lateral clearance on both sides of a multi-lane highway, look what that means. Whether it's a 4-lane or a 6-lane highway, basically the factor is 0. There's no factor that you have to worry about. But if you have less than 12 feet of total clearance, both to the median and to the right of the multi-lane highway, let's say you've only got 2 feet on each side, which is a total of 4 feet. Then for a 4-lane highway, your factor is 1.8, and for a 6-lane highway, it's 1.7. Okay. Then there's the median type table, which is really simple. If your multi-lane highway is divided, your factor is 0. There's no factor at all. But if it's undivided, if you have an undivided highway, and some multi-lane highways are only divided by, say, a double yellow line, and that's it. And then there's 2 or 3 lanes in either direction on either side. If that's the case, then your reduction factor is 1.6. Then you have access frequency. And what this means is how many access points per mile on the segment that you're evaluating, how many access points are there per mile? And this one can have a major impact on your reduction in free flow speed, to the extent that if there's over 40 access points, this means driveways and left turn slots, openings, those kinds of things. If there's 40 or more, that can reduce your speed by your free flow speed by 10 miles per hour, pretty substantial reduction. And what this is all about, this is why I use that term called friction. All of these access points require vehicles to slow down and in some cases even stop to make a turn, or vehicles are jumping into the traffic flow and maybe without a big enough gap. And so vehicles have to slow down to allow vehicles to come in from the driveways and so forth. So they can have a pretty substantial effect. So what you need to do now is to calculate the analysis flow rate, which is the same for the freeway segment. And then you have to, when you do the heavy vehicle, you have to take into account, in order to do the analysis flow rate, you need to use the heavy vehicle factor. And that's the analysis flow rate equation, which is equation 6.7, which I have up here. Remember, you've got your volume, you've got your peak hour factor, the number of lanes, and this heavy vehicle factor. And the heavy vehicle factor is equation 6.9 down here. You still use that for multi-lane highways, and that's where it's saying you still use those same heavy vehicle factors, whether it's level or rolling terrain, or whether you have to do it for a specific grade. It's still the same for multi-lane highways. And then calculating density, this equation 610 is still the same equation that you use for multi-lane highways. And then you can determine the level of service either from table 610. In some cases, you can, the table 610 or figure 6.4, those were the ones, let me go back to those. I showed those earlier. There's table 610 and 6.4. You can use those depending on the data that you have, the data that you're given in the problem. You can use those to be able to look up your level of service calculation. So let me get back to where I was. So you can determine the level of service. So those are let me just stop there for a second, see if anybody has any questions. That there are some similarities between freeway segments and multi-lane, but there are some basic differences as well. And we'll go over a few problems that will highlight those. But any questions at this point? Okay, good. Don't see anything in the chat. So, okay, I've got a few slides here that that I also want to go over. There's one problem in your homework where we kind of get into these things. This is figure 615 from your book. I think it's interesting to look at this. These are graphs that show percent of daily traffic against time of day. And on top, this is an intra-city route, and on bottom is an inter-city route. So in other words, the intra-city route is a route that's in a busy metropolitan area, within a busy metropolitan area, and an intercity route is one of those maybe rural corridors that connects two cities. Okay. Now, the typical weekday is the solid line, and a typical weekend day is the dashed line. So if you think about the freeways around San Diego, and maybe even they're getting back to it now, even with COVID and everything. COVID changed things, but if you think about pre-COVID, or even as traffic is recovering now, this is pretty typical. There's a morning, see at 6 a.m. here, there's a morning peak, then it drops off. Then there's a much smaller peak around lunchtime, and then there's an evening peak. And generally, and this is true in San Diego and true in most metropolitan areas, generally the PM peak, the evening peak is a little bit higher than the morning peak. Traffic's a little bit worse in the evening than it is in the morning. That's pretty typical, but this is, and then of course, between 12 a.m. and 5 a.m. in the middle of the night, traffic's really low, okay? So you can see this is pretty typical, the way traffic works. Then if you look at weekend traffic, it's pretty typically, the peaks are less, and the peak, there really aren't defined peaks in the morning and the evening. There's one kind of in the afternoon, and then it kind of tails off. On the other hand, if you go to an inner city route, what you find is that the traffic on a weekday, the solid weekday traffic here, kind of looks a little bit like the weekend traffic in the city, right? It kind of grows during the day and kind of peaks towards the end of the day. Kind of peaks towards the end of the day. I'm looking at the solid line. But weekends, in some cases, the inner city route, they can have even more traffic on the weekends because people are traveling from one town to another, more so, in some cases, more so on the weekend than they are during the week. So I think these are instructed to just kind of capture the kinds of traffic flows that are typically seen on these kinds of routes. There's also seasonal traffic variations. And now look, we've changed the parameters here of the figure. Here it's months of the year. In the previous slide, it was just hours of a single day. This is months of a year. And then this is the monthly average daily traffic as a percent of the annual average daily traffic, okay? So in other words, basically what this is saying, on a business route, traffic grows in the summertime a bit. It's a little bit higher in the summertime than in, say, where we are now in the springtime, typically. But for recreational access routes, some recreational access routes really exceed and grow in the summer months when more people are on vacation. Again, COVID kind of changes all this, but this is typical. There are situations that don't follow this along here. A good example of one that would look very different than this, or at least maybe have two peaks in it, would be a ski resort. You'd have a peak back here, starting in like late November and peaking through February and March. This peak would move back here. And then a lot of ski resorts do attract people in the summertime as well, but they would probably have their highest peaks back here and maybe lower peaks over here in the summertime. But the point is that depending on the facilities that you're looking at, you do need to pay attention potentially to seasonal traffic variations so that you can plan for it. And then I have one other slide that I think is useful, and it'll be useful for one of your homework problems. And this is a slide that shows the highest 100 hourly volumes in a year. It's figure 617 in your book. And as a matter of fact, the problem in your book directs you to the wrong figure, and I corrected in the homework problem as I describe it in your assignment. But basically what this says is the hourly volumes as a portion of the annual average daily traffic, and the number of hours annually with those volumes or greater. Basically what this says is that if you probably don't want to plan for either a freeway or a highway segment to pass the traffic with no congestion, if that congestion is only going to happen once or twice a year. Way back here, you can see that you'd have to plan for a much higher volume if you were going to be doing it here, versus if it's going to happen 100 times a year. Yeah, you probably want to make sure you have at least that capacity. And as you'll see when you look at some of the other some of the problems and so forth, it's very typical to plan for the level of volume at the 30 hours per year. If it happens, if there are 30 hours spread throughout the year when the traffic is at that level, maybe that's what you ought to be planning for. That's kind of a rule of thumb. And so then that leads to a couple of equations that talk about the K factor here is the design hour volume divided by the annual average daily traffic. And then you can get the directional design hour volume equals K times the directional distribution factor. This is where some freeways are pretty much 50-50. Or highways or freeways, the traffic that goes in one direction ends up coming back that same direction, let's say, and so the amount of traffic in either direction is very similar. But there are some routes where that's not the case, and that the directional distribution factor might be more like 60-40 or 65-35, that kind of thing. So these are a couple of equations that you use on one of your homework problems. Let me just check something real quick here. Just want to see if I got now. That's right. Okay. All right. Let me just hang on one second, guys. I want to pull something else up. Let me see if I can find it. Yeah. Sorry, guys. I want to spend a little bit of time going over, before I go over those problems on multi-lane highways, I want to go over the two-lane highway, just spend a little bit of time on the two-lane highways. So basically, what I want to cover on the two-lane highway characteristics is just kind of the qualitative stuff. No equations, no calculations, just generally so that you have some familiarity of the capacity characteristics of a two-lane highway. Obviously, two-lane highways, one travel lane in each direction, and they're most often undivided. They're used for lower traffic situations. The free flow speeds can range between 45 and say 65 miles an hour, because a lot of these roads are in the backcountry where there's relatively little traffic, and so vehicles can safely travel at higher speeds. They have very wide-ranging design standards, which are oftentimes controlled by the terrain as much as anything else. If you're back in a rolling hills or mountainous country, sometimes it's really hard to put a long tangent section in because of the terrain that you have to negotiate. It may have signals, and possibly some two-lane highways will have stop signs, and more you might even see roundabouts on these kinds of highways as well. And then to pass a vehicle, you have to use the opposing lane unless there are passing lanes provided, and there are in some cases. So when you look at the level of service, not that you're going to be doing any calculations, but I think it's important for you to know that if you're going to be determining the level of service for a two-lane highway, you have to consider the volumes in both directions, not just one. For multi-lanes and for freeways, we're looking at flow in one direction, but for two-lane highways, you have to use both. And terrain can have a much higher impact on the level of service and of two-lane highways because the terrain can have major restrictions on passing sight distance. And if your passing sight distance is restricted and passing opportunities are restricted, that definitely has an impact on level of service for two-lane highways. Base conditions, 12-foot lanes, still the same thing. Shoulder widths of 6 feet. Couple of other things here. Capacity for a single direction is about 1,700 passenger cars per hour, and this is nothing that you have to, remember here for those. But I think it's just worth going through and just looking at two-lane highways. Like this is where passing is constrained on two-lane highways because you've got your double yellow line here. Passing's not allowed. Well, why isn't it allowed? Because there's not a long enough tangent section. If a car's coming, that's a blind curve up ahead, right? And if you're moving in this direction and you got a car in front of you want to pass, there's not enough room to do it. And the same sort of thing happening here. You can see this road is in mountainous terrain. There's lots of curves. It's going to be constrained for passing. On the other hand, this is a nice long tangent section. So on this side, you can pass because you've got a broken line. So you've got plenty of room. On the other hand, on the opposite side, it's solid, which suggests that maybe you've got a curve or a hill coming up in the opposite direction. But here you've got a passing zone. And then in some two-lane highways, you'll find passing or climbing lanes like this one here, which are just, they're not lanes that are continuous. They're just, they're there for relatively small stretches to allow people to pass by slower moving vehicles or trucks. So anyway, that's basically, I think that's about all I really wanted to call. The only other thing I would mention is that the level of service on two-lane highways is really about passing opportunities. If there aren't very many passing opportunities, you're going to have a lot of followers. They use this term followers on a two-lane highway, which means you've got a slow-moving vehicle. People are going to start lining up. If you've ever driven on two-lane highways in the backcountry, you've probably experienced this, where there's a slow-moving vehicle, there's no passing opportunities, and the line of cars behind them just continues to grow, which can turn into an unsafe situation because then people start making, dangerous maneuvers to pass because they get frustrated being behind a slow vehicle. So in that case, you have to provide maybe even a pullout and try to encourage slow vehicles to move over, that sort of thing. So that's about all I wanted to cover on the two-lane section. I thought I had those slides in the same one here. That's why I had to switch it out there real quickly. I realized I didn't have the two-lane highway slides in this deck, so I had to switch it over there. So hopefully that was helpful. And then there won't be any problems on two-lane highways other than maybe a couple of true-false qualitative questions on the midterm, and in the review, I'll highlight those if we go there. But there is a section in your book on the two-lane highways, and if any of you end up working in transportation and work for agencies that have any rural areas within them, it's an area that you may want to take a look at in the future if you end up working on two-lane highways at all. All right, so let's move on to some problems. Any questions before I get going on the problems for the multi-lane highways? I got a question here. Oh, yeah, the slides that I just went over for two lanes. Yeah, I need to upload those. Oh, Even these slides I'm going over. Gosh, that's the second time. I'm going to take care of that right now. I have them, I posted them, but this issue of when I put in class slides, I have to go in and publish them. I can't schedule them to upload at a specific time. So I forget to do it. So there you go. But what I'll need to do is also add those the Multilane slides as well. So I just uploaded the slides that I'm going over right now in Canvas. So that's taken care of. All right. So the first problem I want to go over is example 6.3 in your book. And it's basically just calculating the free flow speed for a multi-lane highway. So if you read the problem, 4-lane undivided highway, okay, that's important. 2 lanes in each direction has 11-foot lanes, that's important. 4-foot shoulders on the right side. There are 7 access points per mile, and the posted speed limit is 50 miles an hour. What is the estimated free flow speed? So basically, we're using equation 614. This equation down here. Here's one thing that I didn't highlight on the slides. It's mentioned in your book, and this is something that you need to be aware of, and that is that they tell you that the posted speed limit is 50 miles per hour. Well, it's stated in your book that the free flow speed for base conditions is generally 5 miles an hour over the posted speed limit, okay, right here. So the BFFS that you would use in this equation is 55 miles per hour, not the 50 that's posted speed limit, okay? That's specifically described in your book. I probably should have highlighted it in the slides, but this problem makes it very, very clear, this example here. So then you have to go and do your lane width adjustment. So if you go back to table 6.3, which is in the freeway section, because it's exactly the same, if you have 11-foot lanes, the adjustment is 1.9 miles per hour. And then if you go to table 611, which is in the multi-lane section, what you do is you use the total lateral clearance is equal to the 4-foot shoulders, and because it's undivided, you use 6 feet for the left side clearance, because the highway is undivided right here. So you use the 4-foot shoulder plus the 6-foot, which gives you a total of 10. And if you look at table 611, and you have 10 feet of total lateral clearance, the adjustment is 0.4 miles per hour. And then if table 612, that's the real simple one, because it's an undivided highway, you use an adjustment of 1.6. If it was a divided highway, that adjustment would be 0. And then you have to kind of interpolate a little bit in table 613, because there are 7 access points per mile, and so if you kind of do a little interpolation in table 613, you end up with 1.75 miles per hour as the adjustments for the access points using table 13. So basically, you just plug all of these right into the equation. 55 minus your lane width adjustment, minus your total lateral clearance adjustment, minus your median adjustment, minus your access point adjustment, and you get your free flow speed of 49.35 miles per hour. Bottom line is, because of the more restrictive roadway characteristics, the free flow speed is reduced by a little over, or between 5 and 6 miles per hour. So that is, that's significant. That's a noticeable difference in the free flow speed of this particular multi-lane highway. So that's example 6.3. Now 6.4, example 6.4 is a little bit more involved. You go beyond just calculating the free flow speed. So I actually have this on 2 slides here, this problem, as you can see. So you have a 6-lane, this one is a divided highway, 3 lanes in each direction, and it's on rolling terrain with 2 access points per mile, 10-foot, it has 10-foot lanes with a 5-foot shoulder on the right side and a 3-foot shoulder on the left side. So you're already figuring certain things out here. You don't have to go into those tables with specific grades because they tell you it's rolling terrain, okay? It's 2 access points per mile, so you've already got that. It's 10-foot lanes, so you've got that. And it's a 5-foot shoulder on the right, 3-foot shoulder on the left, so that's a total of 8. So TLC is 8. The peak hour factor is 0.85, and the directional peak hour volume is 3,400 vehicles per hour. There are 7% single unit trucks and 3% tractor trailer trucks in the traffic stream. No speed studies are available, but the posted speed limit is 55 miles per hour. So first thing you got to do, free flow speed. You want to calculate it using that same equation 614. You have everything you need. The BFFS is 55 plus 5, which is 60. The lane width, because they are 10-foot lanes, the adjustment is 6.6 from table 6.3. Using the total lateral clearance of what do we have here? 5 and 3, which is a total of 8. The adjustment is 0.9, as you can see from here. And then the adjustment for the median is 0 because it's a divided highway, not undivided, it's divided. And then the adjustment for access points, they told you there's 2 access points per mile, it's 2 per mile, and so that's an adjustment of 0.5. You put all of that in, 60 minus 6.6 minus 0.9 minus 0 minus 0.5, it gives you a total of 52 miles per hour. That's your free flow speed. So now what they're asking for is not to stop there at free flow speed, but to determine what the level of service is. So you need to, in order to be able to do the level of service, remember you've got the speed, now you need to also get your analysis flow rate and then use those in order to do your density calculation. So the analysis flow rate equation, you go back to equation 6.7. They gave you V, the volume, which is 3,400. They gave you the peak hour factor, which is 0.85. They gave you the number of lanes in each direction, which is N. But then you need to calculate the heavy vehicle factor, but they gave you that it was rolling terrain, which is 3.0 from table 6.5. So you put all of that, and then they also gave you the one thing they don't show, they just kind of put it in here. They gave you the percentage of trucks, right? Because in the problem they said there was 7% single unit trucks, 3% tractor trailer trucks. A little deceiving there because that makes you think you have to use those grade charts, but you don't. This is more just for the percent of trucks, that's where you get the 10% here. So you calculate your heavy vehicle factor, put all of that in there, and you end up with an analysis flow rate, or V sub P, of roughly 1601 passenger cars per hour per lane. So now you do need to check, the thing is that this analysis flow rate, 1600, is greater than the break point, which we said for multi-lane highways, the break point is 1400. So it is greater. So the S that you use, the speed that you use in your density calculation, is not going to be equal to the free flow speed that you calculated earlier. It's going to be modified based on equation 612 here, right? So in order to do equation 612, you have to use equation 613 to calculate the capacity. And you have everything you need in that equation to be able to do that. The only thing that you really need to add is to the equation is the free flow speed, which you already calculated at 52, right? We calculated it right here at 52. So you put that into the equation, you end up with the capacity being, or C equal 2040. So then you go back to equation 612, and you substitute everything in. You've got the free flow speed, you've got the capacity, you've got the analysis flow rate. And so you substitute all of those values into the equation, and you end up with a speed of 50.5 miles per hour. So if you used the free flow speed, which was 52, the calculation wouldn't be correct. So now you have both of what you need for equation 610. You've got the analysis flow rate of 1601. You've got the speed of 50.5. You do the calculation, you end up with 31.7 passenger cars per mile per lane. And if you go to you can go to table 610 and determine that that's level of service D, because it's between level of service, the maximum density for level of service C is 26, and it's over that, and the maximum density for level of service D is 35. So 31.7 falls in between those two. And you can also use figure 6.4, because you've got your free flow speed of 52 miles per hour. You've got the flow rate of 1601. So you can use that figure instead of doing these calculations here. You can use that figure to determine what the level of service is. You can do it either way. You can either do the calculations of the capacity and the speed and ultimately the density, or you can use the figure to determine what your level of service is. This process is obviously more precise than just looking it up in the table, where you have to kind of eyeball it a little bit. Any questions on that problem? This is a multi-lane capacity, highway capacity problem that's similar to the freeway problems we did, but obviously using the appropriate equations, and but ultimately getting to the same point, which is a density calculation and the level of service. Okay, I've got one more problem that I thought I would go over, which is a practice problem. Practice problem 6.3. Now, this is a problem that includes, you're calculating the level of service, but it has, you need to deal with a specific grade on this one, as opposed to rolling or level terrain, okay? So it's just got, like, I guess, one more level of complexity. So this is the one where you fill in the boxes in the practice problems in your book. And so what we have here, undivided multi-lane highway segment. So it's undivided, that's important. 2 11-foot lanes, that's important, in one direction. No shoulders, and a 55-mile-an-hour speed limit, okay? So that's important, and the fact that there's no shoulders is important as well. So this highway segment has 40 access points on a 1.25-mile, 2.5% upgrade. So lots of access points and a substantial grade that it's dealing with. During the highest 15 minutes of traffic flow within the peak hour, there are 755 vehicles, and 12% of these are heavy vehicles with a 70-30 mix of single unit and tractor trailer trucks. So what are the estimated speed, density, and level of service of the upgrade? So, well, you just got to dive in and get started. The first thing that they have here is, let's calculate the free flow speed. So in order to do that, the free flow speed at base conditions, they gave you 55 miles an hour as the speed limit. So you use 60, 5 miles an hour above. The lane width adjustment, because it's an undivided, the lane width adjustment, because it's 11-foot lanes, the adjustment's 1.9. For the total lateral clearance, it's 1.3, because the total lateral clearance equals 6, because there's 0 right shoulder, which is given, and that's the directions on that particular table. The median adjustment is 1.6 because it's undivided. And then finally, you've got the 40 access points divided by 1.5. And so using that, you end up with an 8 mile per hour impact based on table 613 for the 40 access points in 1.2 miles, okay? So you take all of these values and you pop them into the equation, you end up with a free flow speed of 47.2 miles per hour. So remember, here's the speed limit, 55 miles per hour. So the base condition free flow speed is 60, but because of all these restrictions, look at where that gets you, particularly, as I mentioned before, these access points. These access points can have major impacts on your free flow speed. So the free flow speed in this section is actually under 50 miles an hour. It's 47.2 miles per hour. So that's the first part. So now you need to determine the analysis flow rate, but in order to do that, it's going to be a little bit more complicated because you've got a specific grade. It says the length of the freeway segment is on an upgrade of 1.2 miles per hour, 1.25 miles at 2.5%. So it's a grade that's less than or equal to 3% that extends for more than 1 mile. So you have to use the extended segment analysis. So then you end up with using table 6.8 because that's the one where you've got the 70% single unit and 30% tractor trailer trucks with a 12% heavy vehicles for a length of 1.25. So if you do all that, you end up with the ET factor of 2.6 at a 2.5% grade with 10% heavy vehicles and 2.35 grade with 15% heavy vehicles. So you have to interpolate that. And when you do that, you end up with, a total of, you end up with a 2.5, somehow I missed the value that it equals to, but it's basically 2.50. If you do the interpolation off that table, you get 2.50 as your E sub T factor. You've got the 12% here. So you do the calculation for your heavy vehicle factor and you get 0.85. So you need that to put into equation 6.7 here. And so the other thing is that you take the value of the highest 15 minute volume, you multiply that by 4 on top for your volume. So you end up with the 755 times 4, and you divide that by the number of lanes, which is 2, and the heavy vehicle value that you just calculated, and you end up with 1782 as your analysis flow rate, 782 passenger cars per hour per lane. And so here, once again, your analysis flow rate exceeds the breakpoint of 1400. And so based on that, you have to use your equations 613 and you have to use equation 613 and 612 in order to get the speed calculation that you're looking for. So once again, on the equation, what is this, 613 here, the only thing that you have to add in here is the 47.2, which is the free flow speed that we calculated on the previous slide. And once you do that, you end up with a value of 1944. So now you have everything for equation 612. So you put everything in. You put in your free flow speed, both here and here, your capacity here, your analysis flow rate of 1782 here, and your and your capacity here as well. You crank that all out and you end up with a speed of 44.7 miles per hour. So now here's your density calculation, which is the analysis flow rate of 1782 divided by S, which gives you 39.9 passenger cars per mile per lane. And now this is, this density corresponds to level of service E, because the interval for level of service E on table 6.2 is from 35 to 45, and the minimum and maximum densities for level of service E. And we're at just right around 40. So the bottom line is this problem here, because of all the restrictions that you see, all of the things that have an impact on flow rates are happening. There's restricted lane widths, there's a bunch of access points, there's a steep grade that is going to slow the trucks down, there's a fair number of trucks on this road. All of those things are working to get you to a level of service E, which is just under capacity. So this roadway segment is operating at a much lower level of service than some of the other ones that we analyzed. So I think with these problems here, let me go ahead and stop sharing. I think with these problems and the ones we did last Thursday, you have everything you need certainly to go through and solve the two problems for your group assignment, which is due by Friday. A reminder that Thursday I will have a Zoom. I'll send out a Zoom invite as normal. I'll be online the whole time. I'll establish breakout rooms for any groups that want to use them. You don't have to. You don't have to come in for that class time at all. Just like last time, you can decide how you want to get together as a group, however you want to do that. But if you want to use that class time to do it and get it over with and turn it in, you're more than welcome to do that. And there will be a breakout room available for your group to use on Thursday. And then the homework will be due the following week on by the end of the following week on April 2nd. I'll adjust the due date on that. And so that is basically it for chapter 6. I think when you do the group assignment and then we come back and we do the review, you'll be well prepared for the midterm on both chapters 5 and 6. So that's what I had for you today. It pretty much took the entire time. It's just about 5:15 now. So if there's any questions, fire away. Otherwise, I may or may not see you on Thursday. I'll give you the opportunity to use that time should you want it, should your group want to use it. But if you don't, I'll just look for you to get together with your group between now and the end of the week and get the assignment, the group assignment turned in by Friday at 4. Okay, thanks everybody.